We're continuing now in chapter 5. We're getting 5.2, and that's about a new concept called inner product spaces. Now again, even though it's a new concept, it's going to be kind of built on our old concepts, which is really a big part of the beauty of linear algebra. So the concept we're learning, the new concept, is called inner product spaces, and inner product spaces, basically it's when we did, back in the previous section of 5.1, so we looked at things like length and distance and angles, and we extended them from the regular plane, like like you did in geometry. Extended them to 3 dimensions, which makes sense, but it also extended it to 4 dimensions, 5 dimensions, n dimensions, which didn't really make sense, but we extended the concepts. And here we're going to go even a step further. We're going to take it even further. We're going to go not just to Rn, but to general vector spaces. And we're doing this by using the idea of an inner product of 2 vectors. So we're taking these concepts of length, distance, angle, all kind of stuff, and extending it not just Rn, which was abstract enough. We did that, last section. We're going to extend it to general vector spaces. Now, so what is this scary, inner product? Well, first of all, we've already seen an example of inner product, and that's the dot product. The dot product that we did, in the last section, in regular good old Rn. Now, we call this dot product the Euclidean inner product, meaning that a dot product, we're going to view it now as just a specific case or a specific example of an inner product. I mean, it's the same thing. Potatoes, potatoes. You could say that the inner product is a generalization of the dot product concept, or you could say that dot product is a specific case of inner product. Same thing. Like I say, potato, potato. So, but we do want to avoid a little confusion. So we're going to use some notation here. Let me just when we talk about a dot product, the good old fashioned dot product for Rn, we're going to write it like this: U dot V. That's the Euclidean inner product for Rn, also known as the good old dot product. If we're doing this an inner product in a general vector space, not Rn and not the dot product, we're going to write it this way. This sort of brackety. They're not square brackets, but they're pointy brackets. U comma V, and that's going to be a product. So this is just how we're going to write it. If it's a dot product, we write it up this way up here. If it's a general one, we just write it this way. Either way, the inner product is defined the same way that a general vector space is defined. And let's just get right to it. So this is the definition of an inner product. So U, V, and W, they're vectors in a vector space V. And C is any scalar, so scalar is just a good old real number. And an inner product on V is a function that associates a real number, and the name of that real number is U comma V, pointy bracket U comma V, with each pair of vectors U, V. That's sort of a backwards, it's almost a backwards way of saying it. Meaning because really what we're saying is that we take 2 vectors U and V, we put them in this dot product machine, not dot product, this inner product machine, and they're going to spit out a real number. So that's kind of what we're saying. And any function that does this is called an inner product if it satisfies these 4 conditions. So U comma V has to equal V comma U. U comma V plus W has to equal UV plus UW. So this has to be kind of linear, if you will. Now, C times this product U comma V is the same thing as CU comma V. Now, that's really important to distinguish. When I multiply a scalar times a vector, the scalar kind of gets distributed into all the components. You see what I'm saying? But this is not a vector. U comma V here is not a vector. It's a inner product, which really means it's just a real number. And finally, V comma V has to be greater than or equal to 0, and v comma v will equal 0 if and only if v is the 0 vector. So any vector which inner producted with itself has to be greater than or equal to 0. By the way, we saw that with dot products that they were always greater than or equal to 0. They weren't necessarily equal to 0, but they're always greater than or equal to 0 if you dot producted something with itself. Anyways, the vector space V is called an inner product. A vector space V that with an inner product is now called an inner product space. So this vector space V, which we used to just call, hey, nice little vector space, because it now has an inner product, so we call it an inner product space. So it's a very distinguished, very elite type of vector space. And whenever a inner product space is going to be referred to, we always assume that the scalars is a set of real numbers. Now notice it says assume, because in theory it could be other things, but right now we're limiting our course to just scalars being real numbers. So the first thing I want to show is that the good old-fashioned Euclidean inner product for Rn, affectionately known as the dot product, is an example of an inner product space. You just want to establish that fact, and that we established pretty simply, because the dot product means you multiply. So U is a vector, U1 comma U2 comma dot 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 comma UN. V is a vector, V1 comma V2 dot 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 Vn. U dot V is U1 V1 plus U2 V2 dot 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 plus UN Vn, like we've seen before. And this is going to follow, we know right away this is going to follow all four axioms. How do we know that? We know that from Theorem 5.3. Now, I know what some of you might be saying, what is Theorem 5.3? It's been so long since we've seen that, so here it is. Just to refresh your memory, we did this in the previous section. If U, V, and W are vectors in Rn, and C is a scalar, then these are true. U dot V is equal to V dot U. Something we showed this already with dot products. U dot V plus W equals U dot V plus U dot W. C of U dot V is equal to CU dot V. It's also equal to U dot CV. We're not even asking for that much. V dot V is the magnitude squared, which so since it's a square, it's definitely greater than or equal to 0. And V dot V is always going to be greater than or equal to 0. And V dot V is 0 if and only if V is a 0 vector. With 5.3, that pretty much covers everything that we wanted. We have this UV equals VU. We have this sort of U of V plus is kind of, I'm going to call it like a sort of a distributive kind of deal. U comma V plus W is UV plus UW. C times UV is CU comma V, and V dot V is V comma V is greater than 0. Basically, all the criterion, the four criterion that we're looking for, were satisfied in Theorem 5.3 of the previous section. So yes, the Euclidean inner product for Rn, otherwise known as the dot product, does satisfy the conditions of an inner product. And it's not a shock, because I would imagine that the dot product kind of inspired this whole idea of inner product space, historically. Anyway, let's look at some other examples. So here's a different inner product for R2. So here's what we're going to say. U is the vector U1, U2, like always, because we're in R2, so it's just two components. V is V1, V2, again, just two components. U comma V, instead of being U1, V1 plus U2, V2, it's U1, V1 plus 2 U2, V2. So this is similar, a little similar to the dot product, but a little different. So let's go through everything step by step. We want to show that UV is equal to VU. Well, UV is going to be U1, V1 plus 2 times U2, V2. But that's equal to V1, U1 plus 2 times V1, U2, which by definition is V comma U. So we see that first that first, I'm going to say that sort of commutativity. So it reminds me of like commutativity. That works. Next, u comma v plus w. Well, again, u comma v plus w. That's u1 times v1 plus w1, because that's what the right, plus 2 u2 times v2 plus w2. Now I can sort of distribute things here. These are just real numbers. These are just real numbers now. So this is u1 v1 plus u1 w1. That's 2 u2 v2 plus 2 u2 w2. And now I can separate out. I could just reassociate everything, or reorganize everything, and I get this is equal to u1 v1 plus 2 u2 v2 plus u1 w1 plus 2 u2 w2. But this, by definition, is the inner product u comma v, and this parenthesis, by definition, is the inner product u comma w. So you see that second property works. The next one we want to show is that if C is a scalar, any scalar, so C times u comma v, that's C times u1 v1 plus 2 u2 v2. But I could just bring now these are real numbers. I could just bring the C into the parentheses. So this is C u1 times v1 plus 2 cu2 times v2, and that by definition is cu comma v, not the dot product, but the inner product, this newly defined inner product. And finally, because the square of a real number is always non-negative, v comma v, well, that's going to be v1 squared plus 2v2 squared. I'm adding two positive things, or at least two non-negative things. So of course it's going to be greater than or equal to 0. And this is equals 0 if and only if v is equal to, if only if v equals 0, because the only way the sum of two squares, or not two squares, but a square plus a double a square, the only way that could ever equal 0 is if v1 is 0 equals 0 and v2 equals 0. That's the only way these real numbers can ever be 0. But if v1 is 0 and v2 is 0, that means v is the 0 vector. So there you go. And we have a new function. It's defined in a new way, yet it is the good old-fashioned dot product. I'm sorry, I can't believe I said that. It satisfies an inner product. So yay. Now, of course, we could have generalized this further to do an inner product. UV is C1 times U1 V1 plus C2 times U2 V2 dot plus Cn times U2. In our example, C1 would have been just 1, and Cn, well, n was equal to 2, so Cn would just be 2 in the example we just did. But we could have done this more. By the way, this is called like you ever hear the expression like a weighted average? So the scalars here are called weights, because they sort of weigh. They give each vector more weight or less weight. A good example of a weighted, when I say weighted average, like if you have, let's say you're taking a class and this test is 10% of your grade, and that test is 15% of your grade, and this assignment is whatever, 20% of your grade. So that's like a weighted average. You see what you got on each thing, but each one is weighted differently. Another example of weighted average, by the way, is your GPA, because it's weighted by how many units were in the class. Moving on to example 3. A function, here's an example of a function which is not an inner product. So we're looking at R3 now. So U is U1, U2, U3, V is V1, V2, V3, and now our inner product is U1, V1 minus 2U2, V2 plus U3, V3. And axiom 4 ain't gonna work, because if I do V comma V, I'm gonna get, so let's say V is 1 comma 2, 1, 2, 1. That's my vector. So V dot V is, or V comma V, I should say, is 1 times 1 minus 2 times 2 times 2 plus 1 times 1, which is -6. And -6, last time I checked, is less than 0. So there you go. And that's, it's a funny thing. In general, disproving something is easier than proving something. Because if you want to prove something, you have to show why it works for all cases. You can't go through every single case in the world. There's an infinite amount of cases. So you have to really show and make a clear, a cogent, clear argument of why it is works in every case. If you want to disprove something, just find one counterexample. So we found one example where it doesn't work, and that's it. Pound, it doesn't work. Goodbye. So disproving something is a lot easier than proving something. It's just the way it is. They used to say it's easier to destroy a house than to build a house. Now this is interesting. We're looking at this inner product of two vectors, two matrices which are considered vectors in the vector space M22. And so the inner product here is A11, B11, A21, B21, A12, B12, A22, B2. So really, I'm multiplying the upper left times the upper left, and then the upper right times the upper right, and the lower left times the lower left, and the lower right times the. It's almost like if you consider, it's eerily similar to imagine I would take this 2 by 2 matrix and just lay it out flat. It's A11, A12, A21, A22. Just lay it out in a straight line. It would kind of look like a vector in R4, and B would kind of also look like a vector in R4. And this is really just a dot product of two vectors in R4. It's kind of like the same. It kind of it's not the same thing, but it kind of is. And now this idea of being kind of the same thing, we're going to get to that in chapter 6. But I'm not going to give too much away. But they call it. There's a fancy word for it. They call it isomorphism. But we're gonna get to that. Anyways, let's carry on. Here's a nice one. Let's use some calculus. It's funny. Calculus, as I believe, was a prereq for this course. Although, as you see, we're barely doing any calculus. But every so often, we'll throw in a little bit of calculus that as it applies to linear algebra. So if f and g are real valued continuous functions in the vector space of continuous functions in the interval the closed interval a comma b. So here's what we do. We want to say that the inner product of function f and function g is the integral from a to b of f of x, g of x, dx. Now notice, first of all, the important thing to know is that this whole thing here, this whole integral here, this is a real number. This integral here is a real number. So I'm taking two functions, I'm inner producting them, and the result is a real number. It doesn't look like a real number. It looks like this big fancy calculus thing, but it's a definite integral, and the definite integral is just a number. So you have to get it all down. So let's see if it goes through all the properties. So first of all, it's definitely commutative because I'm just FG, GF, same thing. And if I want to distribute this way, this really distributes because once I say f comma g plus h is by definition f of x, the integral of f of x times g plus h. But then I could these are just real valued functions. I could just kind of distribute the f of x into the parentheses, break this up into two integrals, and now break it up into two inner products. So yeah, number 2 works really pretty easily. Here, if I have a constant times this inner product, well, that's a constant times the integral, but I can always bring a constant into the integral. Again, I'm not going to bring the constant twice. I can't bring it for f and also for g. I can only bring it in once. So, but I was able to bring it in for f, and that by definition is cf comma g, according to our new fancy inner product definition. So all these guys are working, and finally, if I have f of x squared is definitely greater than 0 for all x, and f comma f by definition is just f of x squared. Now, by the way, how do I know from calculus? Since we know from calculus that this is greater than 0. Well, first of all, you're squaring something, so which means this is greater than or equal to 0. Now, if the function is greater than or equal to 0, then the area under the curve is going to be either positive or 0. But I never have to worry about the curve dipping below. So therefore, and the only time it's ever going to be equal to 0 is if f is just a flat line. If it's a function f of x equals 0. So So that works. So we see that this work. So this is true if and only if f is a zero function, which everything works the way we want. And that, my friends, is the story. This is going to be the end of part one. And we're gonna do more of this section, but that's it for now. And we'll see you next time. Bye, everybody. It's been loads of fun.